I like this activity. I start most of my classes with this story. I think it's really important that you guys have feelings about numbers, right? So the way that we learn is through our senses, basically. It's almost like feelings. The way we touch, we smell, we taste, we see, we hear. And if you can kind of get feeling into what you're learning, you can really learn it relatively easily. If you don't feel what you're learning, then it's harder to learn. So I like to start with this just to kind of give you a feeling for what numbers are and where they come from. And hopefully that gives you some experiences to work from as we do more abstract things. So as we go through the semester, you'll see that I use this. The way that we learn things typically comes from these sort of 4 steps. And so if you want to learn something, you usually have to have some sort of experience involving that learning. So the first thing you want to do when learning something is sort of derive some sort of experience from somewhere. The best example of this is probably a chair. Right? So I'm just going to draw. My drawing might not be very good here, but I'm just going to draw a chair. Aha. So when you look at that thing, right, when you look at this thing here, I bet you can identify that as a chair, even though you've never seen it before. In class, I often do this by putting a chair in the middle of the room and say, that's a chair. And I say, how did I know that? How did I learn it? I've never seen that chair before. How do I know it's a chair? Well, I have lots of experiences with chairs. And so from that experience, what I can do, all those experiences, I can reflect upon them. So I reflect upon all my chair-like experiences, and then I can abstract from that reflection that this is indeed a chair because it has the form and the look of a chair, basically. And I can even test it, if I want to, by simply sitting myself down on it and say, yeah, that feels like a chair. And that's how we learn, basically. And so when you're learning very abstract concepts, like in this class, like about numbers and stuff, you want to have experiences. We're working with fractions. You want to have experiences with fractions that are very familiar to you, that then you can use to reflect upon and then abstract to do things that are less familiar. So for example, like I know 1/2 plus 1/2 is equal to a whole. You don't really have to teach me that because I know from my experiences, if I have a half a pizza plus a half a pizza, I get a whole pizza. From that experience, I might be able to figure out how addition works with fractions. So notice, how are you going to add these two things? Do you add the numerators and the denominators? Well, if you did that, that would be 2/4, and that wouldn't be 1. So the idea is, from this experience, I might be able to reflect upon it and say, oh, I think I just add the numerators, 1 plus 1, but I keep the denominator the same because when you do that, you get 2/2, which equals 1. So the rule when adding fractions, of course, is first find a common denominator. But if you have a common denominator, all you have to do is add the numerators. And this experience kind of gives me a reason as to why you should do that. Because if I do something else, it doesn't work. Right? So this is this whole idea, having experiences, being able to reflect upon them abstract, and then sometimes test it to see if it actually works or not. And algebra is the main outcome of this. So in this class, as we do algebra, you'll see that I always try to create experiences that you can then reflect upon and abstract to figure out the final answer. And that's a key at being good at algebra in the beginning. And then once you get really good at it, you can kind of throw away your experiences, So when you see this chair, it's not like I really reflect on every single chair that I've ever seen. The form is so familiar to me, I'm just click, it's a chair. And I sit down in it and I use it as it should be used. Okay, so we start with our story of numbers with the philosophy of numbers. And so we start with a very simple question, right? In philosophy, it's like, what is life? What is love? In math, we say, what is a number? And it's a very simple question that has a rather tricky answer. And so to kind of show you why this is sort of a tricky question to answer, let's start with this. So let me just write this down and ask you a question. Is this a 2? So is this a 2? Question mark. Right? So answer that question, and most likely you'd say, yeah, that's a 2. I mean, I've been using that number for a long time, right? It's the number 2. But I'd say, no, it's actually not a 2, right? And that may be confusing at first, but then I say, oh, watch what I do here. So look at that word, very familiar word. And let me ask you this question. Is this a dog? And of course, you say, no, this is not a dog, right? What is this? This is a word that represents a dog, right? So this is a word that represents a dog, which is very obvious to all of us, right? For the same reason, this is not a 2. So the answer to this question is actually no. This is a symbol that represents 2. And once you see that, you see that this question is actually very deep. It is not easy to answer. So this is simply a symbol that represents the number 2, just like this is a word that represents a dog. And of course, in a different language, it has a different word. Just like up here, there are different ways to represent the number 2. So for example, if we talk about the Roman numerals, the number 2 is represented by this symbol, which we all know. And so, no, that's not a 2, just like this is not a 2. These are simply symbols that represent a 2. And so then the question is like, well, where is a 2? Again, a very difficult question to answer. In fact, this question wasn't actually answered to the late 1800s. And in the early 1900s, a mathematical philosopher named Bertrand Russell wrote a book answering this question, what is a number? So for those of you that are interested, you can Google this book. It's actually, you can get it for free online. In fact, I have it right here because I got it when I was in college. And you can try to read his answer. I think it's in chapter 2 here on a definition of a number. And it's very difficult to figure out what he's saying. And so it took me quite a while to understand it, probably a couple of years of mathematics to understand exactly what he was trying to get at. But it's a very deep and somewhat complicated question to answer. But the good news is that we do not need to know what a number actually is to work with it. And that's sort of a philosophical thing. It's kind of like, I don't really need to know what love is to actually engage in it. I can fall in love, even though I might not be able to define what love really is. All right, so I'm going to leave that part there, and let's move on, all right, to how our numbers represented, because this is another interesting aspect of numbers. So when we write down a number, how do we write it down? So we might write down this number here, 21, right? And so when we write a number down like that, we do it, seems almost obvious to us, that's 21. But it actually has a deeper meaning. The real reason why that's 21 is because it has a 1 in the ones place and a 2 in the tens place. So this is really the same thing, you can say if you want, as 2 tens and 1 1. And so this gets really into what I call the technology behind numbers, which is really advanced. And so this is kind of fun because we all learn in elementary school how to represent numbers, but we never really thought about how it actually works and how complicated and useful it actually is. Because we know if you change the position of the numerals, the numeral 2 and the numeral 1, we get a completely different number, right? So if we write a 1 and a 2 there, that's a completely different number. That's 12 things. So what we have here is 1, 10, and 2 ones. Right? Completely different number. Right? And at first, again, it's like, that's no big deal. Right? I've been doing that in my entire life. But now, think about why we use base 10, because this is called, the type of numeral system that we call this is a base 10 positional numeral system. And the interesting part about this is the base 10. So ask yourself this question: why do we use base 10? Right? Why represent numbers base 10? And hopefully you're thinking to yourself, base 10, it's because we have 10 fingers. So this is kind of fun, because if you think mathematics is just about numbers, I'd say, well, do you think mathematics is somehow dependent upon your fingers? It's not really just about numbers, right? Mathematics is really about things and their relationships. And that's why it's really so useful to us, right? Not just about, 1, 2, 3, 4, 5. It's really about the way we represent 1, 2, 3, 4, 5, and then the relationships with each other. And what we can do is we have any sort of things, we can look at those things, and then we can study the relationships with each other, and we can create some sort of mathematics around that. And so this is kind of a fun little thought experiment. Imagine if we met an alien race and how they would count. So they would probably count, the way they count would probably depend upon the number of fingers that they have. So they may not have evolved to have 10 fingers. So if they have 6 fingers, they will count base 6. So if you write a 2 and a 1 like this, an alien race will not see that as 21 things. An alien race would see that, yes, as 1, 1, but this wouldn't be 2 10s, it would be 2 6s, because they only have 6 fingers, right? And so when they look at this thing, that would be 2 6s and 1 1. Which is really, how many things would that be? 2 6s and 1 1. That's really 13 things. Right? So it's kind of fascinating how this technology of the way that we represent numbers actually works. And then you may think to yourself, well, I don't know, is that even useful? Is there any sort of application to that? And that really gets into how mathematics is discovered, because we figured out how to represent numbers using these base numeral systems long before we found a real great application, besides being able to represent numbers, base 10, right? That's a huge feat in itself. But we eventually did find a great application for representing numbers in different bases, and that's the binary numeral system, right? So here, the binary numeral system. And this is the system all of our technology is based on, right? This is just using zeros and ones to represent information. So it turns out all information in the entire universe can somehow be encoded with simply 2 symbols, 0 and 1. And that's an amazing application of these sort of base numeral systems. Okay. So we talked a little bit about the philosophy of numbers. I introduced a sort of technology of numbers, things that you're very familiar with, but don't realize how interesting they actually can be. Now I want to go on and talk about specific types of numbers. And to do this, I'm going to need my calculator. So let me get my calculator up here, because I didn't get that prepared beforehand here. But here's our calculator right here. We're going to use this to kind of solve some problems here. But what I want to do is now talk about the discovery of numbers. So chapter 3, how are numbers discovered? Where do they come from? So you're familiar with lots and lots of different types of numbers, but sometimes when I ask you questions like, well, what does that number mean? Or where do they come from? you really don't know the answer. And so our goal here again is try to develop some experiences for you with numbers to make you more familiar with them. So when we're working with them, uh, it's easier for you to work with them, right? And then when we do algebra, it's easier to abstract from them. So we're going to start, which are called some of the number systems. And so we're going to start with a nice, easy little number here, which is called the number 2. And this is an example of what's called a natural number. So what are the natural numbers? So 2 is an example of a natural number, and it's very easy to give an example of 2. All I like to do is just draw 2 dots and say, that's 2. So that's where 2 comes from. It's a very simple observation that when you want to count things, you have 1 thing, you have 2 things, and then you have, there's a fork here, 3 things. And you want a way to represent that number of things so you can basically count. So sometimes the natural numbers are also called the counting numbers. And so the way we write this down in mathematics is we use a symbol. We use an N with a double bar there. And those are called the natural numbers. And we can actually write them out. They're equal to, we use these curly brackets to represent a set of things. So we write curly bracket, and we start with 1 and put a comma, and then a 2 and a comma and a 3 and a comma. And once we have established the pattern, I mean, you know the next one is 4, right? Then we can just write dot, 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 which means continue on this fashion forevermore. And then we end with another curly bracket. And so that's the set of 1, 2, 3, and then 4, 5, dot, 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 etc. And so these curly brackets, when you write those, the way you say that is defined to be said the set of. So set of. And so we use those curly brackets in mathematics to represent a set. The foundation of mathematics is set theory. Now, we're not going to get into set theory because we don't want to get into that foundation, like be able to actually define what a number is. We want to learn how to use numbers and develop some easier experiences with them. And then some of you guys, if you're a math major, you'll actually get into understanding what set theory is in your second year of your major. But for us, it's just a little bit of notation. The curly brackets means a set, and the natural numbers are like 1, 2, 3, 4, 5, 6, 7, and so on. Never 0 though. So 0 is for kind of a complicated idea. So I always like to remember is like, what are the most natural? What are the ones that we learn how to count with? And the first number we typically learn is 1, and then 2. 0 comes much later. All right, so over here I have what's called a Venn diagram. And this is a way to organize information. So we're going to use a Venn diagram here to organize number systems, basically. So this 2, it's in the natural numbers here. So I'm just write a symbol. So right here, this little circle represents all the natural numbers. So you can write them all in there if you want, 1, 2, 3, 4, 5, dot, dot, dot. But that's the idea. You have the natural numbers. But there are other types of number systems. So the natural numbers are nice. You can count up, but you can't count down. So in order to count down, we have another number system called the integers. And an example of an integer is -2. Now, -2 is a little bit harder to kind of show where it comes from, but it's not that bad. Like, here's an example of -2. You start with 2 things, then you take them away. That's -2, basically, right? You lost 2. So, you might draw 2 dots and say there's +2. And then what's -2? Well, you take them away, like you just X them out. They're gone, right? Or you take 2 things, you give it to a person, and then you take 2 away. There's a -2 action for you. So the integers are like the natural numbers, but you can count up and count down. So for these, we use a strange symbol because you'd think we'd use I, because integers start with I, but we actually use Z for the integers. And that's because this comes from the German to count, which is Zählen. And so this is kind of interesting. In mathematics, we have a lot of different languages being used to do mathematics. And so sometimes those languages, we adopt symbols from them and we use them in our mathematics. And so Z comes from the German Zählen, to count. And the integers look like what? Well, again, we draw a curly bracket. It's a set of, and I'm going to come out a little bit here to the right, and I'm going to write a 0. So it's nothing. And then you can count up 1, 2, 3, and then of course dot, 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 because you see the pattern. We'll end the curly bracket for the set. But remember, you can count up, but you can also count down. So over here, we have what's called -1, -2, and -3, and then dot, dot, dot. And so the integers are a nice little number system that include the natural numbers. So in our Venn diagram, notice here I'll write Z. Here's our integers. And notice how the natural numbers lie inside the integers because they're what's called a subset of, which I don't really want to get into, but they lie inside. The natural numbers lie inside the integers. And so the integers are nice because you can count up and you can count down. In fact, this starts giving way to what we call the number line, which is kind of a cool idea. So the number line, and I know you guys have all seen this before. We introduced this to students at a very young age. And it's just a line with an arrow on either side and it goes out both ways. And you can put some numbers on here. So we like to put 0 on here, 1 on here, 2 on here, 3 on here. And you can go the other way now, since we have the integers, -1, -2, -3, and so on and so forth, right? And now the number line is a very powerful construct because you may think it's rather simple, but notice if you put two number lines together, you can describe a two-dimensional space. So notice this, if you just lay another number line on top of the other number line, and now we have going up 1, 2, 3, -1, -2, -3. Now we have a way to describe a two-dimensional space, basically kind of like GPS, right? So you can give somebody directions how to get from point A to point B. You can even go one step further if you want and give a three-dimensional space by putting a number line that comes out of the page. Okay? And then you can even go further because now that you can describe 3 dimensions, even though you can't visualize 4 dimensions, you can just create another number line. And that gives you a 4-dimensional space. Another number line gives you 5 dimensions, and so on and so forth. So the number line actually gives us a way to describe an n-dimensional space if we need to. And again, you may think, there can't be any application. Right? There can't be any application, but I tell you this, right? Application. You know, for a long time, people thought base numeral systems, what a interesting thing that happens, but there certainly can't be any applications. All information can be represented with zeros and ones. Any applications? I think so, right? So it turns out that what's interesting about this is this is how, in some sense, we organize information to see if it's connected. Right? How does the internet work? How do search engines actually work? Well, it turns out they use this sort of n-dimensional space idea to sort of organize information to see like where you want to go. So if you go to Google and you type something in, how does it know, where to go? Well, it's organized in an n-dimensional space. And when you type something in, it figures out where is the most likely thing it should point to in that nth dimensional sort of space, basically. So it's kind of interesting application. So, it's kind of like, I think it's Netscape. Oh, not Netscape. That's an old term, guys. You don't even know what Netscape is, probably. Netflix. I think of Netflix uses this to sort of organize, what movies we might enjoy. So our recommendation list, basically. Okay, so let's go back here. And so we've talked about the natural numbers. We've talked about the integers. So we can count. We can now count up and down. So what are we missing? So what you want to notice is in the integers, you can add, you can subtract, you can even multiply, but you cannot always divide in the integers. So, 4 over 2 is 2. So that's good. But if you do 2 over 4, that's no longer an integer. So what we need to do is expand this number system a little bit more to get a number system in which we can add, subtract, multiply, and now divide. And so those are called the rational numbers. And so in the rational numbers, we'll be able to add, subtract, multiply, and divide those numbers. And so here, 1/2 is a great example of a rational number. And how would you explain this number to somebody? Well, I like to draw 2 dots We'll draw a green and a red dot. And you can say stuff like, oh, 1/2 of the dots are green or 1/2 of the dots are red. You can even draw a picture and then shade in half of the picture and say that represents 1/2. So there are a number of ways to represent rational numbers to see where they're actually coming from, right? So remember, all this is just like, how did you discover these numbers? Where did they come from? Why are they important? And so now when we write these numbers down, though, it's a little tricky. So we actually use the letter Q to represent the rational numbers, which again, you may think is strange. Why did they use R? Well, you'll see why we use R to represent something else. But Q stands for quotient. So what's a quotient? A quotient is a fancy name for divides. So you can divide two numbers or take the quotient of two numbers. It's really the same thing, right? So it's just a fancy way to say divides. Now, when we write down what these numbers look like, it's a little harder to write them down. You can't actually list them per se. It's hard to list them, basically. So what we do instead is we draw a curly bracket for set, and then we write the number A divided by the number B, so we write A over B, such that, so we draw this line, and that line right there we read as such that A and B are integers. We have to have one little sort of caveat here. B cannot be equal to 0. So if you look up the rational numbers, you'll typically see this definition written down for them. And so it's kind of abstract. So this one, instead of being able to list the actual elements of the set, you actually have to give a description of those elements, which is sort of two ways to sort of describe sets. That's not really that important. I'm not interested in you guys memorizing definitions. What I am interested in is exposing you to ideas that later will come back and be important, especially as you guys get into higher level math classes. So a lot of this lecture is about exposure, but gaining experience also to, what is 1/2? How would you represent that? How would you think about that? So this is a nice number system because, yes, you can add, you can subtract, you can multiply, and you can divide in this number system. And so up here, for the rational numbers, we'll just write a Q. And notice the rational numbers, these are all these numbers right here. They include, of course, the integers, and they include the natural numbers. Okay, so now we ask this question, are there any other numbers? All right, so are there more numbers? And what's interesting to this question is from an application point of view, no, you don't really need any other numbers. So if you're trying to solve a problem that's an applied problem and you have to set numbers to it, all you actually need are the rational numbers, because when you're solving an applied problem, there's always some error involved. So you may only need to know the answer to 5 decimal places. In fact, I believe 5, it might have been 6, but I think 5 decimal places is all we needed to know pi to get from the Earth to the moon. So if you knew pi to 5 decimal places, you could use that in your calculations to figure out how to get from the Earth basically to the moon and back. So from all practical purposes, all you really need are the rationals. But the more interesting thing is there are more numbers. There's lots and lots of more numbers. So we're going to talk about these numbers right here. These are called not rational numbers, but think about it. What would you call numbers that are not rational? And hopefully you're like irrational numbers. So, and remember, you guys should be filling this out as we kind of go here. So we're filling out the activity in the workbook. So we have irrational numbers. And now we don't really think about this in terms of a number system per se, because it turns out oftentimes when you add and subtract irrational numbers, it's not hard to get a rational number out of it. But there's certain types of numbers, and they're ones you're very familiar with. So, the most familiar one for you guys, I might pull this up just a little bit right here, is this square root of 2. The square root of 2 here. This is a very familiar number, the square root of 2. Come down. And so think about square root of 2, because this is one of those questions where I ask students like, well, what is the square root of 2? What is that thing? How do you find it? Where does it come from? And so typically what you guys will tell me is, well, you can go to the calculator and you can type in the square root of 2. And I'm like, that's a good idea. So you hit second x squared, pulls up the square root button. You put a 2 in there and you hit enter. And it gives you this, this answer right here. And so you're like, oh, yeah, that's nice. So what's the square root of 2? Well, it's this number 1.414, blah, blah, blah. So let's just write this down here, 1.414, and I'll just write ... for blah, blah, blah. All right, great. So that's what square root of 2 is. But what does it mean? Right? Where did it come from? So first, let's just try to answer, what does that number mean? So what is 1.414? Why is that the square root of 2? Why isn't the square root of 2 1.7 or 1.6 something? Why that number? So think about that for a minute, because if you can give me a solid answer, it just means that you have some good experiences with numbers. If you can't, we're going to develop that experience here in a second. So what is that number? Well, I'm going to write down the answer, right? It is the number you square to get 2. Geez, a little bad there, right? It's the number you square to get 2. And in fact, your calculator kind of tells you that, because if you look at your calculator, the square root button's right behind that x squared button. So if you hit x squared, it takes that asked answer and squares it, and it gives you back 2, because that's what the square root of 2 means. Right? You get out a number. It's a number that you square to get 2. So you can then apply that knowledge. And for example, you take the square root of 3. You'd say, what is that number? Well, that's the number you square to get 3. I don't know how my calculator found it, but I know what it means. Right? And that's going to be very important. That'll be kind of a common theme like in this class. It's like, well, you may not know how the calculator, how the technology works, but you know what it means. Right? And that's the first step to understanding. Know what it means, and then eventually we can get in there and understand how the technology is actually being applied to get the answer. But we need to develop these experiences. So for example, I always like to do what's the cube root of 5? Now this one's a little bit trickier, because when you look at your calculator, you'll notice on the surface, there doesn't seem to be a cube root button anywhere. So if you ask me to do a cube root, I actually usually change that to exponent notation. So this can be rewritten as 5 to the 1/3, where the 1/3 is in the exponent. So if you want to figure out the cube root of 5, I can rewrite this and do 5 raised to the 1 divided by 3. And that gives me the cube root of 5. So I get this number 1.709 blah, blah, blah. And I can tell you what that number actually is. This is the number you not square, but cube to get 5, right? So it is the number you cube to get 5. And I build this all off of my experiences with square root of 2, basically. And once I can do that, then I can tell you all kinds of interesting things about radicals and exponents, which we'll work on throughout the semester. And again, you can check this on your calculator. If you raise this number to the 3rd, you see you get back to number 5. I don't know how it found the cube root of 5. That's a much more difficult question, but at least I know what it means. All right. So I can answer such questions as what is the square root of 2, at least what it means. But do I know where it came from? And so this is a great question, because again, you've worked with this number almost your entire life, but you still may not know where it comes from. Like, how was it discovered? Right? Numbers are kind of nice because you can answer questions like this. You'd simply Google them and you could probably find the answer for the question. But where does it come from? It comes from something you guys are all familiar with, which is called the Pythagorean theorem. And this, again, talks a little bit about how mathematics is discovered. So what's the Pythagorean theorem? Well, most students usually know this coming into this class because we really focus on it in your mathematical education, right? So basically the idea is you have a right triangle. So a triangle with a 90-degree angle on it, and you have three sides. We call the sides A, B, and C. And it turns out there's always this relationship between the three sides of a right triangle, namely A squared plus B squared is equal to C squared. And so we call that the Pythagorean theorem. Now, what's interesting about this is you can say, so like, well, why is that true? And where did that come from? You know, it seems at first like, well, is that just a fact I have to memorize? And I usually tell you guys, like, no, it actually comes from this guy named Pythagoras. And not so much Pythagoras, right? Other people knew about this theorem before Pythagoras, but Pythagoras really popularized this theorem. So that's why it's called the Pythagorean theorem. But there's a story that goes with it. And it's a very interesting story, which tells you how mathematics is discovered. Because students often say to me, like, well, what's your job? I mean, you just teach mathematics? I'm like, yeah, I teach mathematics, but I also discover, research mathematics. And they say, well, there's more to be discovered about how we found everything already. Oh, no. It turns out every time a new technology is developed, there will always be new mathematics to understand that technology. So this is a very good example, because where did the Pythagorean theorem come from? Well, Pythagoras was a guy. He was out looking for knowledge. So he's roaming the world, basically, and he goes over to Egypt. And in Egypt, he finds these people called the rope stretchers. And what do rope stretchers do? Well, they stretch rope. And so he goes out and he watches these rope stretchers. And what does he see? He sees that they have a piece of rope with 3 pegs in it. So there's 1 peg, there's 2 pegs, and there's 3 pegs. And their rope it's all connected, right? So you have 3 pegs and rope in between. And what do the rope stretchers do? Well, they take that rope and they stretch it. And when they stretch it, they create right angles. They stretch that rope, and that rope automatically creates a right angle for them. And that's how they construct lots of their buildings, like the pyramids. How do you lay out the foundation? Well, you have to have a nice square for the foundation. How do you construct right angles? Well, one simple way to do that is simply take a rope with 3 pegs in it. Now, Pythagoras knew those pegs can't just be anywhere. If you just put pegs in a rope, right, you have a rope here, and you should put pegs in it, you put them real close to each other and you peg them down, you are not going to get a right triangle. Okay, so he knew that was the case. So there must be something very special about these distances here, A, B, and C. And so he took a couple of these ropes, because there were several of them that they would stretch to get right angles. Some were small, some were large, and he looked at the lengths, A, B, and C, and he realized there's a relationship between A, B, and C always. A squared plus B squared is always equal to C squared. And that's how he discovered the Pythagorean theorem. Right? It was already being used to do something, and Pythagoras came along and said, I think there's a general rule, there's a general law, there's a theorem applied that's being applied here. And that's where the Pythagorean theorem came from. So it just came from some sort of application that was already being used, and it just took a person to come and look at it and kind of analyze it and come up with sort of a general theory about it. And that's how lots of mathematics is discovered. Sometimes there's an application, people come in, they analyze it, and they come up with a mathematical theory that models it. And then sometimes it goes the other way, though. Sometimes the mathematics is there, they discover it, and then later on, there comes an application, like with the binary numeral system, right? That application came much later after its discovery. Okay, so that doesn't actually tell us, though, where square root of 2 comes from. So to do that, it's just application of Pythagorean theorem. So I don't know if you guys can see up here on my wall, you guys see those little tiles? They're squares, basically. And then let me see if I can get my finger in the right spot here. There. If you take that diagonal right there to the other side, right there, take the diagonal across, that's actually a square root of 2 unit length. So that's where square root of 2 comes from. It comes from a simple observation that if you have a right triangle of unit length, so 1 unit here, 1 unit here, it turns out this side has to be the square root of 2, because 1 squared plus 1 squared is equal to c squared by the Pythagorean theorem. And so 1 plus 1 is 2 is equal to c squared. If you square root both sides, square root of 2 is equal to c. So it's all around us, really. Whenever you see a perfect square, that diagonal is a root 2 of the length of the lake. Right? So it's everywhere. So it comes up very naturally when you're constructing or building things. And so it's a number that is all around us all the time. It kind of pops up. All right, so that's the story of square root of 2. And it's an irrational number. Now, that's a little bit harder to show. So, why is this number, put a question, why is it not equal to some integer over some integer? So we're not going to go through why that is. But if you Google it, you can actually Google why is square root 2 irrational. They'll show you this little sort of proof here. And it turns out if it was rational, it'll turn out that A and B are both even and odd, which that possibly can't be. A number is either even a number or it's an odd number. But that's the idea. So you assume that it's true and turns out that it's not true. And so that's what we call a contradiction in mathematics. It's just a logical way to show something, to prove something. Basically, it's kind of like, if I know I live over here, how can I prove I live over here? Well, go over there. I never found where you lived. Well, you must live over here, right? We call that proof by contradiction. Right? But it's kind of a cool little way to discover square root of 2 using the Pythagorean theorem. Now, are there other irrational numbers, which are numbers that are not rational? And it turns out there are lots and lots of them. Some of the ones we're going to work with in this class are pi and e. So let's talk about pi, and then we'll talk about e over here. So the number pi, over here we can write, if you want, pi for pi. And what's that number equal to? Well, I know what it's equal to. It's equal to 3.14 blah, blah, blah. Your calculator has a button on it, actually, that will tell you what it is up to so many decimal places. So on your calculator, if you hit second raised to, there's a pi button there. And if you hit enter on that, it says it's 3.1415, blah, 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 right? So it goes on actually forever and ever. It turns out an irrational number, when you look at its decimal expansion, always goes on forever and ever and never repeats. I don't know if you had this in your math classroom in high school. They had the number pi going all the way around the room up towards the ceiling there. And so it goes on forever and ever and ever, never stops, and it never repeats. Whereas a rational number, if you look at its decimal expansion, either terminates, which means it stops, or it repeats forever. Right? So it's kind of a nice way to classify the difference between rational and irrational numbers. Rational decimal expansions either stop, they terminate, or they repeat. Irrational, they go on forever and ever, and they never repeat. But 3.14, blah, 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 where does pi come from? All right, so we usually are familiar with the number because we've been using it for a number of years. But where does it come from? So think about that. Where does pi come from? And hopefully you're like, oh, yeah, it comes from a circle. So when we study circles, the number pi naturally pops out of it because the definition of pi, so what's pi actually equal to? What's the definition? Well, the idea is you just take the circumference of the circle. So you take any circle, measure the distance around it. So take a tape measure and just measure the distance around it. We call that the circumference. All right, so that's the circumference of the circle. So maybe I should write that down. Circumference, which is like the distance around the circle. And then we divide it by the diameter, d. And then so there's a center here, and the diameter is the length across the circle through the center. Right? We call that the diameter. So this is actually the geometrical definition of pi. So if anybody ever asks you what pi is, you say, oh, it's simply the circumference of the circle divided by the circle's diameter. That's the definition of pi. And so this definition leads to a couple things. It leads to a formula for the circumference of the circle. So what's the formula for the circumference of the circle? This is equal to 2 pi r, where r is just the radius of the circle. So notice here, d, which is the diameter, is just 2 r. And r is called the radius of the circle. It's just the distance from the center to the circle, basically. And so that's probably an important formula. We don't use a ton in this class, but you will use it in other math classes. So if you don't know that, you may want to kind of put that in the back of your mind. Another great formula to know about circles is how do you find the area of the circle? So a circle has area, has space on the inside. How do you find that space? How do you measure it? Well, it's pi r squared. And I'm not going to go into where that actually comes from, but if you want to Google that, there's some great YouTube videos out there showing you where this actually comes from, because you can actually break up this circle into little triangles and put it back together and create a rectangle out of it. And we know the area of a rectangle is the length times the width. So it's kind of a cool sort of demonstration. So if you've never seen that, maybe Google or go on YouTube and write down, finding the formula for the area of a circle, and you'll find that. All right, so that's enough for pi. So if someone shows you pi, if you know it's 3.14, and you're like, oh, it comes from circle stuff, you're good to go. You have some good experiences with pi. How about for e? So where does this number e come from? So this is kind of a weird number. I call this the natural number. So the natural number. It also has another name called Euler's constant. Okay. Euler was a famous mathematician in the 1700s, right? So Euler's constant, or Euler's number, right? So it's Euler, like oil, basically. But I always call it the natural number, and it looks like this. It's equal to 2.718, blah, blah, blah. It goes on forever and ever. Your calculator has a way to find it. There are a couple ways to do this. I like to hit second ln. So if you hit second ln, it pulls up the e to the button. I put a little 1 there. And so e to the 1 is 2.718281828. And it actually goes on forever. It actually doesn't repeat, even though it looks like it might be repeating. It doesn't actually ever repeat. And this is a very important number because it's a number that naturally comes out of when you study things that grow or decay. So grow/decay. So if you study something like money, and you want to understand how money gets bigger, how it grows, or it decays, gets smaller, this little e will pop out of it. Or if you study population sizes, so how do populations grow or decay? If you do that, this number will pop out of there. Or if you study illness, right, how does the flu spread or how does COVID spread? That number E will naturally pop out of that study. So it's a very important sort of powerful number. In some sense, I'll tell you this, it's sort of the secret for us to be able to do computation. So the ability for us to compute things actually lies in this number E, which we'll talk about as the semester go on. But for us, if you know the natural number, what it is, 2.718, blah, 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 and you know it comes from growth and decay somehow, you know more than most people. All right, now I want to make sure that I got everything that I wanted to talk about on here, which looks like I do. Okay, so our story's not done though, guys. So what have we done so far? I've just talked about these irrational numbers over here. Okay, so over here are these irrational numbers. But notice there's this whole sort of piece right here in our Venn diagram at this sort of bigger rectangle right here. And that bigger rectangle, it represents what are called the real numbers. So let me come over here and talk about the real numbers. And so the real numbers sort of complete our picture. The real numbers, these are the rational and irrational numbers combined. Right, so rational and irrational numbers. So when you smush those two numbers together, those two types of numbers, you get what are called the real numbers. And we use the letter R for this with the sort of double bar there. And the way we write down the real numbers is we draw a curly bracket and we write X such that negative infinity is less than X is less than infinity with a curly bracket. And I always tell you guys, this little symbol here, it's super tricky at first to remember what that is. And I tell you guys, hold up your hand, your left hand here, and make the little less than symbol with it. And I know it's less than because if you just turn it, it's the letter L, right? It's the letter L right there. And so this means less than because it looks like the letter L. So on here, maybe make a little note. It's like the letter L. And that's the key to remembering that little symbol there is less than because it looks like the letter L, basically. And then the other one, of course, will be greater than. So you have to have a way to kind of remember some of these symbols at first. And so I like to use, little silly tricks because, once I have the trick down, then I'm good to go. And then I can forget the trick because then I remember it, right? That's how learning kind of works. I make myself a little learning experience and I can use that experience to remember what it is. We also like to use that number line, right, to represent the real numbers. And so we can put 0 on there, 1, 2, 3, -1, -2, -3, so on and so forth. Oops, let me get down here and do this. Do that. Make that negative better, so -2. And you can even put other numbers on here because, that number pi right here, 3.14, it's a real number. And you can even put, what's another, square root of 2. So I'll put that one right about here, so square root of 2. Right, it was 1.414 or something like that, right? So there's square root of 2. You could put, I put it in the wrong spot, guys. Let's put it right here. Square root of 2, it was 1.414. There it is. So the square root of 2 right there. And then, you put E on there, 2.718. So there's E. So it contains all these irrational numbers, positive or negative, so even the fractions like -1/2 is over here. All the numbers on the number line are considered real numbers, basically. Okay, so that actually ends the story for this class, right? We're most interested in working over the real numbers, but there's one last class of numbers that's kind of nice to see, and they're called the complex numbers, or if you like, the imaginary numbers. I'm going to call them the complex numbers because that's how they're known today. But 100 years ago or more, they were called the imaginary numbers. So what are the imaginary? Oh, and let me put the real numbers on our picture, guys. So our real numbers are right here. I put it right there. So the real numbers, all this stuff, this big rectangle right here, are the real numbers. And of course, they contain every other number system. But there's this one last number system here, the giant rectangle on the outside. This kind of completes our story in this class. Always tell you guys, it's always good to go one step further than you need to go, and then the stuff behind is a little bit easier. So the last step involves this I equal to the square root of -1. And this is called the imaginary number. Right? And you say to yourself, imaginary number, right? What does that mean? Does it not exist? It's not real, so it's not a real number. It's imaginary. So what the heck is an imaginary number? So let me tell you a little bit about the imaginary number because it has a great story to it to kind of understand where it comes from. So it actually isn't too hard to show. So the imaginary number comes from, people trying to understand how to solve simple equations. So x squared minus 1 equals 0. What are the solutions to this equation? Well, somebody that's doing algebra would say, well, I think I'll add 1 to both sides. And I get x squared equal to 1. And then I'll just square root both sides, and I get x equal to, and then remember, it's plus or minus the square root of 1 when you square root both sides, really. And so x is equal to plus or minus 1. And that's my answer. And so notice, if you go back and you plug a 1 in here, and you square it, 1 squared minus 1 is 0. Or if you plug a -1 in here, and you square -1, it becomes positive 1. Minus 1 is equal to 0. So those are the two solutions. So someone's like, great, I found the solutions to that equation. Now, what if I want to solve an equation that looks very similar, but instead of -1, we put +1? What if I want to solve that equation? And then someone says, well, you can't solve that equation. Why? Well, they said, look, you're squaring something. So when you square something, it has to be positive because we know if you take a number and square it, it's always positive, right? Because a positive times a positive is positive. And if you take a negative times a negative, it's positive. So how can you take a positive thing and add another positive thing and get 0. You can't. So what we should say is that there's no, and I'll put a kind of a blank here, solution. The little blank. And I say, well, yeah, the people that were doing this, like, oh yeah, I guess there's no solution because a positive plus a positive equals 0. But somebody says, well, hold on a sec. Let's not let ourselves like, let's not let like what we think is true be the truth. Let's make sure we verify this, because I have the power of algebra that I can use to try to find a solution. So that person says, all right, well, let's subtract 1 from both sides. So we get x squared equal to -1. And then just like we did over here, let's take the square root of both sides. So we square root that side, square root that side. So x is equal to then, and then it's plus or minus, right? So plus or minus the square root of -1. And so that person says, no, there is a solution. I just wrote it down. It's plus or minus the square root of -1. And the person that says there's no solution says, well, hold on. There is no such number as square root of -1, right? That doesn't exist. And the person that solved said, yes, it doesn't exist. It's imaginary. And that solves the problem for both of them. So the person says, yes, it doesn't exist. It's an imaginary number. So it's like an imaginary solution. But it's nice because you do get a solution. It's just not real. It's imaginary. And in fact, it's so imaginary that we don't even use the square root of -1. We just write the letter I to represent the imaginary number. And so the person that said there is no solution eventually agrees to say, well, it's not that there's no solution. There's no real solution. So you'll see this pop up from time to time in textbooks. Say, oh, no real solution to this equation, which means there is an imaginary solution, but no real solution. So for a long time after this discovery, people called these the imaginary numbers, basically. But eventually, we found an application. Right? Just like those binary numbers, where we have the ability to represent all information in the entire world with zeros and ones, so the binary numeral system, right, which is the foundations of our technology. We found very useful applications for complex numbers, right, or the imaginary numbers. They actually turn out to model electricity, right, electricity and magnetism. Right, and they model all kinds of other stuff. This was one of the more interesting ones. Because we use electricity and magnets all the time. Electricity is used in all the devices around us, and the magnets in our engines that drive our cars and our automobiles, our planes, and everything like that. It also is used to sort of understand how temperatures change, basically weather, and so on and so forth. It turns out anything that you can apply what's called a vector to, you use basically what are called imaginary numbers to model it. And so we changed the idea from imaginary about 200 years ago, I'd say, to complex numbers. Because it's not that they don't exist, they're just very complex in a way. And like I said, if you have anything that's with a vector, basically, you use these types of numbers to represent them. Right, so that we're not going to talk too much about the complex numbers, but I thought it'd be nice for you guys to go one step further. Oh, and I guess I should write them down too. So we use the letter C to represent the complex numbers, which is pretty clear why, right? C, complex numbers. And then we do a little curly bracket here, and then A plus BI, such that A and B are real numbers. And so that's how those are all the complex numbers. And you can even represent these. I don't want to get too deep into this, but you can have what's called a real number line and an imaginary number line. And so if you want to represent what is 1 plus 2i, you go over 1 on the real part and go up 2 on the imaginary part, and you draw a little arrow to that point, and that's 1 plus 2i. And when you work with these numbers, when you add, subtract, multiply, and divide them, you see there's a natural sort of arithmetic that moves that little arrow around. It makes it longer, makes it shorter, rotates it, basically. And so it's used to model what are called, vector flows. So if you have, basically, if you want to think about this, think about like the air in your room. If it's moving around, you can kind of measure at each point how it's moving. And so what happens at that point, you get a little arrow. If the arrow is really long, the air is moving a lot. If it's very short, it's not moving as much. If you put all those arrows together, you can actually see how the air is flowing around in the room. Okay? And so this number system gives us a natural way to measure that phenomenon. Okay, so my time is about up, and there's one last thing here, right? So I keep forgetting this picture. Final thing, we put a C right there. And there's the final Venn diagram for our number systems, the natural numbers, the integers, the rationals, the reals, and the complex numbers.